The European Space Agency is working to take humans beyond low Earth orbit and deeper into the cosmos. Our next destination on this journey is the Moon. The 1960s and 70s were an incredible era for space exploration. The Ranger missions from the United States took close-up images of the Moon before eventually impacting the surface. NASA's Surveyor missions demonstrated a controlled soft landing at the surface of the Moon and tested the properties of lunar soil to prepare for future human missions. A series of Soviet landers and rovers visited a number of locations, performing scientific investigations, driving across the surface, and returning samples to Earth. But the pinnacle of this period of exploration was Apollo, and the arrival of humans at the surface of another solar system body for the first and only time in history. Looking back now, though, we see that only a tiny fraction of the Moon's surface has been explored, all on the side of the Moon that faces the Earth and in a region close to the equator. We've also discovered that all of the samples we have returned to Earth are from an unusual region, with a complex and exotic chemistry of potassium, phosphor, and rare earth elements such as thorium. The vast majority of the Moon has yet to be explored, including the entire far side. One thing that we can say for certain is that if we want to understand the Moon, then we need to go back there. Now, after decades of waiting, an armada of missions from around the world, including ESA's Smart 1, have returned to explore the Moon from orbit. Looking down from above, these missions are providing a wealth of new data, bringing a new understanding and raising new questions. They are giving us a global insight and preparing for new missions to the surface led by China's Chang'e 3. And the next wave of missions to the surface? Where might they go? The next destination will be unlike anywhere we have been before, the extreme and alien landscape of the lunar South Pole. Here, we find areas of permanent darkness and extreme cold, where water, ice and other chemicals can become trapped. And as we come up from these lowlands, we see towering peaks, basking in near constant light. On these polar mountains, the sun rarely sets below the horizon, providing the potential for near continuous solar power and a spectacular view over the rugged and cratered landscape below. In 2009, the L-Cross mission blasted water and other chemicals out of a permanently dark crater in the South Polar region, allowing it to be observed by nearby spacecraft for the very first time. We also now know that there are nearby locations with similar cold conditions. Is there water here too? If so, how much is there? Where did it come from? And what can it teach us about the origins of water and life-forming chemistry on Earth? This water may have been delivered by comets and asteroids impacting into the surface over billions of years. It may even have been created at the surface of the Moon. We now know that protons thrown out by the Sun in the solar wind arrive at the lunar surface. Here, they react with oxygen in minerals to create a thin layer of water. These water molecules can be lifted by the Sun's heat before falling again to the surface. Over time, these particles may move to the polar regions, where they are trapped by the cold conditions. And as we stand at the pole, with the Earth in view, we can point our antennas to the sky to search for faint signals from deep out in space. But radio noise from the Earth is too loud and blocks out many cosmic radio sources. But as we move over the horizon, the Earth sets out of view. The noise disappears and a new kind of radio sky emerges. We see our galaxy and the planets as never before. And beyond, a quiet radio hum, a signal from the cosmic dark ages more than 13 billion years ago, when the first cosmic structures were formed. And now, beneath us, the moon as we see it today, scarred by craters formed by billions of years of impacts, and the largest and the oldest of these, the South Pole Aitken Basin. Formed by a powerful impact around 4 billion years ago, many believe that its formation marks the start of a dramatic period of bombardment onto the Earth and the Moon, an era called the Cataclysm. This era is recorded on the Moon's scarred surface, and its end coincides with the appearance of the earliest observed traces of life on Earth. In the coming years, we will see explorers at the lunar poles, exploiting the extended sunlight for power and performing research to benefit life on Earth and to understand our place in the universe. This will begin with small robotic missions to understand the environment and prove new technologies to pave the way for the future. We will then move on to increasingly ambitious missions with humans and robots working together, learning to live and work at the surface, and performing new and important scientific research. This new exploration will be achieved not in competition as in the past, but through peaceful, international cooperation. Eventually, we will see a sustained infrastructure for research and exploration, where humans will live and work for prolonged periods. Here, we will put into practice the lessons of years on the International Space Station to establish a facility akin to those that we see in Antarctica today. In the future, the Moon can become a place where the nations of the world can come together to understand our common origins, to build a common future, and to share a common journey beyond. A place where we can learn to move onwards into the solar system. And perhaps in the future, at a sun-bathed peak at the lunar South Pole, at the edge of a crater, we will learn to access and utilize resources from deep below in the dark. Zooming in, closer and closer, we see water ice molecules trapped in the cold. A source of hydrogen and oxygen, essential for sustaining human life and for rocket fuel. Fuel to propel us further into the solar system and on to the next destination of our journey into the cosmos.